In this video, we are going to observe the motion of a falling object, and then, with a little help from the momentum principle, we will analyze the forces acting upon this object. First, we will record a video and use Tracker to record the object's motion. We will then construct a computational model using Newton's second law to replicate the observed motion. After some analysis, we may realize that revisions must be made in order to improve this model. Lastly, after the analysis of these models, we will discuss some what-if questions. In this experiment, we analyze the motion of this bear being dropped. Using Tracker, we were able to plot the position versus time graph modeling the motion of the bear. This can be observed in the upper right-hand corner. We follow the same steps as discussed from previous labs to analyze this video. It is important to note the axis was rotated so that the positive x direction is here, vertically aligned with the screen. Next, we created a computational model using VPython to mimic the motion of the falling object. The most important part of this model was the use of Newton's second law, as shown here. We follow the same steps as previous experiments with a few important additions. As usual, we set the initial conditions of the experiment, as displayed here. The ball mass, the ball position, which started at the origin, making this value vector 0, 0, 0, and the ball velocity, which was dropped from rest, also making the vector 0, 0, 0. Here we added G, or the force that pushes on the bear as a result of the gravitational force of Earth. We also indicated the J hat vector to orient the model, determining which way was up. We added in the effect this force from Earth has on the motion of the falling object by adding that the F net is equal to the mass of the ball times this given G value, as displayed here. Now, if we run this model, we can gain some initial data. Now, if we analyze the data collected, we will notice a few problems. First, if you look at the graph of the Tracker data, the actual data, and the VPython data, the predicted data, we can see major discrepancy. We can also see that the final position displayed in the Tracker data is much different than the predicted final position displayed in the model data. With the poor quality of the data received from our first model, we know we must make some edits, this time accounting for all the forces acting upon the falling object, not just the gravitational force. We will now indicate to our code an additional force acting upon the object when it is falling. This force we can call drag or air resistance, and it is equal to the velocity squared, as indicated by this line of code. We also indicate that the total net force is equal to W, the force from our previous model, plus the drag force acting in the opposite direction. It is also important to note that the drag force is different for every object. In this case, with the falling bear, the constant is equal to 1.2. Now, if we try running this additional model, we can expect better results. With the revised model and this data, we can see now that we have a much more accurate representation of the actual motion of the falling object. We can see that we even have both very similar final positions. Here's a side-by-side comparison of the two models and their data. Now, let's talk about a term called terminal velocity. What this means, at a certain velocity, is that the drag force is going to be equivalent in magnitude, but in the opposite direction of the force of gravity acting upon the object due to Earth. At terminal velocity, the object will be moving at constant velocity because the acceleration, or change in velocity over change in time, is equal to 0. At constant velocity, the slope of the line should be linear, or constant. We can see here that our second computational model data represents this. Now, let's examine a possible scenario. Would the terminal velocity of the object change if it were initially thrown downward rather than starting from rest? We can tell you the answer is no. But why? In order to examine this what-if question, we analyze the data of both a model starting at rest, which we've already done, and a model starting with an initial velocity of 10 in the negative direction, which represents the throwing force. Now, analyzing the data gained from running each model, in addition to just the position and time, we can gain the velocity, the change in position over change in time, and the acceleration, the change in velocity over change in time, at each point. As we stated before, terminal velocity is when the acceleration is reaching zero. From our data, we can determine that both models are approaching the same velocity as acceleration approaches zero. Then, terminal velocity is not changing, regardless of the initial velocity. This is exactly what we see in the graphs of our data. Regardless of the initial velocity, both accelerations tend to zero and both velocities tend to around negative 2.1.